Hello everyone, I'm Paul and today we're solving problem 909, snakes and ladders. This one is medium, but it's tricky. Here I will show you two efficient solutions. One is a pattern that you will find useful for future problems, and the other one is sort of like a unique solution for this one. So keep watching. The first challenge here is to understand this problem. Basically, we are given a board such as this one, and we start at square 1. And each time we roll a dice and we get a value, and we move the amount of squares corresponding to that value. So for example, if we roll the dice and we get the 2, we move from 1 to square 3, and so on. Now, for example, if we get a 1, in this case we move to square 2. And here we have a ladder. In this board we have ladders and snakes. Given that here we have a ladder, we need to move from square 2 to square 15. We move to the end of the ladder. And similarly, if we move to square 17, meaning we move to the head of a snake, in this case we must move from square 17 to square 13, to the end of the snake. And the goal for this game is to reach from square 1 to the last square, in this case 36. And the goal for this problem is here. We need to return the least number of dice rolls required to reach the last square. And if it's not possible to reach the last square, we return -1. For example, if we have this full of snakes, maybe we get stuck in some loop and we can never reach the last square, and in this case we return -1. Now another thing to consider is that if we are in a square with no ladder or snake and we move to a square with a ladder or snake, we then move to the end of that ladder or snake. And if here we have another ladder or snake, let's say that 15 takes us to 27, in this case we don't go to 27 automatically. We roll the dice and we continue. That's what it says here. Now, in case you didn't notice, we can think about this as a graph. Let's say we are here at the source at node 1 and we are trying to reach node 36, the last node. Well, we can think about this as if we are building an adjacency list and we have a directed edge from 1 to 15, and from 1 to 3, from 1 to 4, from 1 to 5, and so on. And with this in mind, we can build an adjacency list for this entire graph, and then we can find the shortest path from the source from 1 to the final destination node 36. We can do this with a BFS. Now remember that in BFS we move from one node to every adjacent node. Here we have directed edges. So we move from here to here, for example, from here to here, from here to here. And from here we move to every adjacent node also. We move here and here, for example. And these are levels. This is level 0, this is level 1, and this is level 2, and so on. So for example, if we are in the first node, we are here at level 0, and from here we move to 2, meaning to 15, okay, because the edge from 1 to 2 doesn't exist. We will go from 1 to 15. So we are right now in 15 at level 1, and from 15 we go to 13 because the edge from 15 to 17 doesn't exist, but we have an edge from 15 to 13, and here we are at level 2. Next, from 13 we go to 35. Now we are at level 3. From 35 we move to 36, and now we are at level 4. So finally we return 4, and this happens to be the shortest path from 1 to 36. Now there are two ways to solve this, and I will show you both. The first one is a standard strategy to find the shortest path in a unweighted graph with BFS, and the second one is sort of like a unique solution, a unique and optimized solution for this problem. So I recommend you to learn both. And in these solutions we will also use some math, because in one solution we will use the values in the squares. We will call this x, and we will use this to get the corresponding row and column, and in another solution we will take the row and column and we will use this to get the corresponding value in the square. Okay, so this has a row and a column, and we can do this both ways. We can use row and column to get the value, or we can use the value to get row and column. I will show you how to do both strategies. We'll do this for one solution and this for the other solution. Let's say we are at row 5 and we are at column 4, and we want to get this value. We don't know that this is a 5, but we want to get the corresponding value for this cell. First we can add the row part, so we can take the total number of rows we have. In this case we have 6, minus the current row, which is 5, minus 1, 0, times the length of one row, which in this case is 6 also. So 0 times 6 is 0. So we will call this n minus the current row minus 1 times n. And this in this case is 0. And for the column part, we first are checking if n minus the current row minus 1 is odd or even. If it's even, we add to the result the column part, which would be, we'll call this c modded by n plus 1. So 4 modded by 6 is 4, plus 1 is 5. So 0 plus 5, this is 5. So the corresponding value for this cell is a 5. Now let's say we know this is a 5, but we want to get the corresponding row and column. Now for the row part, we'll take this value minus 1, meaning 4. We'll call this x minus 1, and we will divide this by n. We will round down this value, and this is inverted. So this means that we need to reverse this. We can reverse this like this, n minus this minus 1. So in this case, 6 minus 4 divided by 6 minus 1 is 5. And here we are at row 5. So this makes sense. And for the column part, we first need to check if this row from bottom to top is even or odd. So we need to reverse the current row and check if it's even or odd. So n minus the current row minus 1 modded by 2, in this case, is 0. So here we will use x minus 1, meaning 4 modded by n. So 4 modded by 6 is 4. And here we are at column 4. Now if we were here from bottom to top, we would be at row 1. And 1 is even. This means we would need to reverse this part. And remember, we can do this like this. We add n at the start minus all of this stuff minus 1. Now that's it for the math. I know this can be tricky if you have never seen these calculations, but I recommend you to think about this slowly, step by step, and you will find the logic. So now we'll go the first solution, the standard BFS to find the shortest path from 1 to 36 in this case. This will have a time and space complexity of big O of n squared. N equals the length of the board, and first we will store shortcuts. We will create a map called shortcuts, and in here we will store each shortcut. But first we need to create a function to get the square with a row and a column. This is the math part we saw before. So here first we are processing the row part, so result equals n minus r minus 1 times n, and if n minus r minus 1 multiplied by 2 is 0, we add to the result the column part for even rows. So result plus equal column multiplied by n plus 1. Else, meaning if the row from bottom to top is add, we add to the result the column part corresponding to n minus c multiplied by n. And finally, we return the result. Next, we create our map. We'll call this shortcuts. This is an empty map. Now we'll iterate the grid to add the shortcuts to the map. So for I in range n and for j in range n, if board at I j is different from 1, meaning if we have a shortcut in this cell, shortcuts at get square ij equals board ij. And now we can build the adjacency list. So to build adjacency list, for this adj equals default dictionary, and we will set a default value for every key of an empty array. So we use list here, and for I in range from 1 up to n square, and for j in range from 1 up to 7. Remember, here we are working with square values, with the values for every cell. So if we are out of bounds, meaning if I plus j is bigger than n square, we break this loop. And if we are in bounds, if I plus j is in shortcuts, adjacency at I dot append shortcuts I plus j. Else, meaning if I plus j is not in shortcuts, we do this adjacency at I dot append I plus j. Okay, so if we are in a shortcut, we take the shortcut, and if we are not in a shortcut, we append the value corresponding to the current dice roll. So now with this, we can go to step 3, which is do a BFS to find shortest path. For this, we'll create an array. We'll call this dist, and every value in this array will be initially infinity, so float inf, and this is times n square plus 1 because n square is included, and we'll have a queue we will use a deck for the queue because we need to pop elements from left, and we'll start with the node 1. This is the source, and the distance to the source, meaning to 1, is 0. And while we have something in the queue, we take the first node with queue.popLeft, and for every neighbor in adjacency at the current node, if the distance to the neighbor is greater than the distance to the current node plus 1, in this case we need to update the distance to the neighbor. So dist at neighbor equals dist at the current node plus 1. Because think about this, let's say the distance to this neighbor is infinity, and we are trying to find the shortest path. So if the current distance plus 1 is smaller to the distance to the neighbor, we just update the distance to the neighbor with the current distance plus 1. And if we do this, we also want to append to the queue the current neighbor. And now with our distances array, we can return the minimum distance to n square. But this might be infinity. And if this is infinity, this means we never reach the end, because we have some cycle in the board. And if we never reach the end, we want to return -1. So we return this if this is different from infinity. And if this is infinity, we return -1. So this is it for the code. Now let's submit this and see if it works. And as you can see, this works. And I recommend you to try to learn this algorithm because it will be useful for another BFS shortest path problems. And now we will go with another more efficient and specific solution for this problem. So keep watching. Remember that in the previous solution we were building an adjacency list and we had to store the shortcuts in a map to build that adjacency list, and from that we were able to run a BFS to find the shortest path, but we don't actually need this adjacency list. We can do this more efficiently, and here I will show you how. First, n equals length of board, and here we will work basically with the values in the cells. So we will create a function similar to the math function for the previous solution, but here we will create a function to get the position for some value, for some cell value, and this will return some row and column. And here we need to implement similar math as before, so row equals n-1. Remember that this is to reverse stuff. Here in between we need to do x minus 1 divided by n, and this is it for the row part. And now for the column part, if n minus r minus 1 modded by 2 is 0, column is x minus 1 modded by n, else column equals n minus x minus 1, sorry, this is x minus 1 modded by n minus 1. Okay, we are also reversing this part if the current row is add. So now we have the math part and we can start with the BFS. So we'll have a queue, and for this we'll use deck to pop elements from left, and we'll start with a tuple This will include 1 for the current node, meaning the source, and a distance corresponding to this source, which is 0 for the first node. Just to be clear, this is node distance, and we will have a set. We'll call this scene. We'll use this to detect cycles, because remember, we can have cycles here. And now, while we have something in the queue, node distance equals queue.popLeft, and for every value in the range from 1 up to 7, remember that here we are working with cell values. And if we are out of bounds, meaning if node plus x is greater than n square, we break. And if we are in bounds, the next node will be the current node plus x. And from this we can get I and j with our previous function. So this is get position from next. And if board I j is different from -1, meaning if we have a shortcut here, we take the shortcut. So next equals board I and j. And if next is the final destination, meaning if next is equal to n square, we return the current distance plus 1. And finally, this is the BFS part. Remember that we can have cycles, so if not next in scene dot add next, and queue.append a new tuple with next and the current distance plus 1. And finally, if we end this loop and we never reach the destination, we return -1, because this means we have a cycle somewhere. If next is never equal to n square, we return -1. So this is it for the code. Now let's submit this and see if it works. As you can see, this works, and it's more efficient than the previous solution. It has the same time and space complexity. It's big O of n square, but here we are not using an adjacency list and a map for storing shortcuts, so this code is more efficient. If you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.